After we have dealt with the simplest application of Laplace method with the Stirling formula, we now turn to a bit more complicated example. So in this lecture we will discuss the details of evaluation the following asymptotic estimate. So consider the integral, which is shown on this slide, and of course from the form of the integral it's immediately obvious that it exists as a well-defined function only for a larger than -1. Suppose that a satisfies this condition, and our question is, what is the asymptotic behavior of this integral at x very large and positive? Again, as on the previous example, we try to understand if indeed our integral represents the integral of the standard Laplacian form. Again, let us recall what is this form, and looking at this comparison between these two expressions, we again see that, first of all, the integration limits do satisfy our requirement. They do not depend on the large parameter lambda, so this check is passed. Second question is, does our function in the exponent have the form which we required, in a sense that large parameter lambda should enter the exponent homogeneously. And at this step we notice that this is not exactly the case, because x in the exponent multiplies only first contribution, and the second seems to be just of the order of 1. So our first step in reduction of our particular integral I of x to the standard form will be to change the integration variable in order to achieve this desired property of the exponential. Again, as we have seen in the previous slide, we will try to change the integration variable. However, in this case, it will be not that simple, because now we will change the integration variable from t to s with some unknown factor a, which we will just determine a posteriori. So now suppose we change the integration variable from t to s, we have some factor a, which is not known for a moment. After we substitute this s as an integration variable, we will find out that our expression in the exponential, here it is, takes the following form. And recall that we will now require from this expression that it becomes homogeneous as a function of lambda. In our case, large parameter lambda is represented by x. So obviously, for this expression to be homogeneous function of x, we must require that this factor, which multiplies 1 over s, becomes unity. So as a result, we have the following equation. It becomes just 1 over square root of x, and correct change of integration variable is t equal s over square root of x. So this way we fix our unknown parameter a, and after this change in the integration variable, our integral, which is just equivalent to the previous form, it now becomes exactly what we need in order to apply the Laplace method. In particular, we see that the large parameter, which now is not x but square root of x, enters exponential in a homogeneous way. And finally, we now try to analyze this function, which multiplies the exponential, and try to find out whether it has some maximum in a certain point in the integration range. So in order to figure this out, we'll write this function separately. This is just minus s over 2 minus 1 over 2s. And in order to find the stationary point of this exponent, we must solve the standard equation, derivative of f at some point s equals to 0. And as a result, this equation can be easily solved, and we find out that maximum of the exponent is achieved at s equal to 1. As you remember, our next step is to figure out what are the properties of this function f of s in the vicinity of the maximum. And for our goals, all what we need is the first non-trivial approximation to this function, that is quadratic Taylor series. In order to find the form of this series, we need to calculate the second derivative. And in this case, it is just minus 1. So as a result, our next step is to simplify this integral, a of x, according to the substitution which we just discussed. So in order to implement our program, what we need to do is the following. So in order to implement our program, we substitute the full function f of s by its Taylor series. So in this particular case, it looks in the following way. And close inspection of this integral immediately demonstrates that actually it again becomes the integral of a standard form, which you probably remember by now. And as such, this integral can be easily evaluated. Again, remember that our final step is to change the integration domain from 0 to infinity to minus infinity to plus infinity. This is again justified by the fact that this integral comes from the tiny region in the vicinity of s equal to 1. And in fact, exact integration range doesn't matter.